Let's look at complex numbers and putting them into a complex plane, both the rectangular and the polar planes. We're going to be able to explain why the rectangular and polar forms of a given number represent the same complex number. So let's begin by defining the complex plane in the rectangular Cartesian system you're used to. And how this works with complex numbers is the real part is plotted on a horizontal axis, what you've also always known as the x-axis. We call that the real axis in the complex plane. The vertical axis is called the imaginary axis, and we use it to plot the imaginary part. So for example, let's take the point 3 plus 5i. What we're going to do is we're going to plot this point by going over 3 on the real axis, 3 to the right, and then up 5 on the imaginary axis. So 3 to the right and 5i up. And when we plot that point, that's its location. So if we call that point Z1, the point Z1 has a real part of 3 and an imaginary part of 5i. If we had a point -2 minus 4i, we're going to go 2 to the left on the real axis, and we're going to go 4 down for -4i on the imaginary axis. So if we called that point Q, that's where it would be located, there in quadrant 3. 2 to the left on the real axis, 4i down on the imaginary axis. So that's how you plot complex numbers on the complex plane in the rectangular system. The first number represents its real coordinate. The second number represents its imaginary coordinate. We're going to talk about an entirely new way of graphing things. Up till now, you've used almost exclusively the rectangular or Cartesian system, which had x and y, where x was a horizontal coordinate and y was a vertical coordinate. Now we're going to use a new system that has two parts also, called the polar system, where it's got an r or radial coordinate that represents the distance the point is from the origin, also called the pole. The second coordinate is called the angular coordinate, theta, and it represents the angle that that point makes if it were on a ray from 0 degrees. So instead of x and y, we have r and theta. So let's take a look at the point 5, 30 degrees. Now you can do the polar coordinates in either radians or degrees, but for our purposes here, I'm going to use degrees. So 5, 30 degrees. So the first thing we're going to do, the radial coordinate is 5, which means we're going to go out 5 units from this pole or origin. 1, 2, 3, 4, 5 rings out. So somewhere on this fifth circle out, this fifth unit out, is where the point lies, and it lies at an angular coordinate of 30 degrees. So from 0 degrees, we're going to go counterclockwise 30 degrees along that fifth ring to find that point. So indeed, the point 5, 30 degrees is right there at a radius of 5 and an angle of 30 degrees. So how about the point 4, 220 degrees? Well, we'd go 4 rings out for its radial coordinate, 1, 2, 3, 4, so it's somewhere on this fourth ring, and then we're going to go 220 degrees from 0 to find its location. So it's 4 out at an angle of 220 degrees. -4, 220 degrees, we would go to this 4, 220, but then go in the opposite direction. So we'd go 1, 2, 3, 4, and along the line, 180 degrees from it. So negative would wind up going in the opposite direction at the same angle. -4, 220 degrees would be right there. So that's how points are plotted in the polar system. R tells us the radius, the distance from the origin or pole, and theta tells us the angle that it makes. Okay, let's develop the idea of how we take something from the rectangular system, which is in an x, y, or real imaginary format for coordinates, and turn it into the polar system, which has r and theta, a radius, a radial coordinate, and theta, an angular coordinate, and translate between the two. Let's take a point 3 plus 4i, which has a real component of 3 and an imaginary component of 4i. And that real part is very much like the x you've been plotting for years, and the imaginary part is very much like the y-coordinate you've been plotting for years. So in that Cartesian, that rectangular system, we go through to the right 3 and up 4. Well, how do we translate that into a polar system? Well, in the polar system, we have a radius, and that radius is going to be the distance from the origin or pole to the point. In this case, that's 5, because 5 is the square root of 3 squared plus 4i squared. We also have, in the polar system, the angular coordinate. What's the angle that that point makes if we're on a ray with the terminal side through that point and its initial side along the positive axis? How much are we going to rotate that? Well, if you go back to trigonometry, we've got a little right triangle here with sides of 3, 4i, and 5. And to find that angle, we could use the inverse tangent of the vertical coordinate divided by the horizontal coordinate, opposite over adjacent. We're going to find theta, the angular coordinate, using the inverse tangent. We're going to find r, the radial coordinate, using the Pythagorean theorem. And indeed, converted into polar form, this is the point with r of 5, because r is the square root of 3 squared plus 4 squared. Oh, by the way, that's the modulus, which is 5. And theta, the angular coordinate, is going to be the inverse tangent of, in this case, 4 over 3, which is approximately 53 degrees. So the point in polar space that's given by the rectangular point 3 plus 4i is 5, 53 degrees. And to plot that, we're going to go out 5, 1, 2, 3, 4, 5. And then we're going to go rotate 53 degrees. Notice how those 2 points look like they're in the same spot. They are. It's just 2 different ways of showing the same information. So that's the complex plane. How to plot complex numbers in both a rectangular system with a horizontal real component and a vertical imaginary component, and also in a polar system where the complex number is represented by a radius and an angle.